studied basic quantum mechanics, you may have studied about light matter interactions. In those light matter interactions, we always considered light to be semi classical. However, if we quantize light, which is called as second quantization, we can understand a lot more phenomena which we cannot understand by the semi classical treatment of light. Also, this particular idea of second quantization of light is important to understand how the continuous variable quantum computing works with the photonic technology. So, in this video, we will learn about the second quantization of light, which is a theoretical framework that treats light as a quantum field. We'll come to what a quantum field is. And it is composed of quantized particles. You may have already heard of these, which are called as photons, and it allows for a comprehensive description of the light's behavior in terms of creation and annihilation operators. If you have done basic quantum mechanics, you may have heard of these. And enabling it enables study of complex phenomena such as quantum optics and more advanced light matter interactions. Now, before going ahead in this particular video, I would like to give you a few heads up. First, that this particular video would be a bit mathematically heavy, so you can skip through this video. And if you are not interested in the physics, you can, of course, go to the important points in this video and copy the important rules and the uh, results without diving into much of the physics. Second, that we will review second quantization of light in this particular video, which is important for the CVQC uh, using photonic technology. Third, we will understand what are creation and annihilation operators and what are particles of these particles and quadratures, etc., which are important building blocks for the CVQC operations. So, to understand this second quantization of light, we need to first understand and review the quantum harmonic oscillator. So, if you have studied classical mechanics, the energy of a harmonic oscillator is given by p square by 2m plus half m omega squared x squared, where p is the momentum of the single particle which is oscillating, m is its mass, omega is the oscillating frequency, and x is the position. Now, when we quantize this particular harmonic oscillator, we convert these scalar physical variables p and x into physical operators p cap and x cap. So, the energy of the quantized harmonic oscillator, that is a quantum harmonic oscillator, is given by p cap squared by 2m plus half m omega square x cap square, where this cap denotes that these p and x are no longer scalar physical variables but are what are called as operators. And the relation between x and p is given by p cap is equal to minus ih bar del by del x. This h cap acts on some of its eigenvector psi, and it gives us some en psi. And this is one of the allowed energy levels of this quantum harmonic oscillator. We'll come to it. Now, to solve this particular problem or to simplify this one, Moreover, before going ahead, we should understand that this x cap and p cap follow what is called as the Heisenberg's uncertainty principle. That is, the commutator x cap and p cap, that is x cap p cap minus p cap x cap, is equal to IH bar. So this is what is followed by these x caps and p caps. Now, let us define another two operators which are related to these x cap and p cap as a cap, which is equal to root of m omega by 2 h bar x cap plus I by m omega p cap, and another operator a dagger, which is equal to m omega by 2h bar by x cap minus I by m omega p cap. Now, using this commutator rule, you will you will easily see that the commutator of A and A dagger is equal to 1. If you don't understand these commutators, what are they? I highly recommend you re- to refer to some basic quantum mechanics book like David Griffiths, or the book by Noreddin. I hope I'm the spelling is correct. Noreddin Zitili. You can refer to these books and understand the quantum harmonic oscillator. Now, as we have defined these transformations A and A dagger in terms of x and p like these, we can also write x and p in terms of A and A dagger. So x becomes equal to h bar by 2m omega A cap dagger plus A cap, and this is equal to I times h bar m omega by 2 into A cap dagger minus A cap. You can easily see this by just simple algebraic manipulation. I am not going through it. Now, using these definitions of A and A dagger and this commutator rule, you will be able to see that H cap is equal to H bar by 2 A dagger A plus A dagger. I leave it on you to derive this. You just simply need to substitute these relations in this particular Hamiltonian equation, and you will easily see that it will fall into this particular notation after factorization. You also need to take care of these commutator rules, that is, A dagger is not equal to A dagger A. So if you take care of the commutator rules and everything, you will reach to this particular form. And by again using the commutator rule, you can also see that this is equal to A dagger A plus half. So this is the energy of the quantum harmonic oscillator in terms of the creation and annihilation operators. And this is the same thing, the energy of the energy operator for the quantum harmonic oscillator in the terms of the position and momentum of the harmonic oscillator. Now, as we have already learned that in quantum mechanics, when an operator acts on its eigenstate, let's denote it by n. I'd earlier written it as phi n, but I think writing it as n makes the notation easy. Then, if this energy operator h cap acts on its eigenstate n, denoted as such, it will give us an eigenvalue multiplied by the same eigenstate, where this n will go from 0 to infinity. Now then, using the right hand side from above, that is this particular equation, we can see that h bar omega a dagger a plus half acting on n is equal to enn, or a dagger a acting on n by doing some algebraic multiplication here, we will see that it is equal to en by h bar omega minus half n. Now, as the right hand side is a number, this thing is just a scalar, it is a number times the same vector n. That means that this is an eigenvalue of a dagger a. En by h bar omega minus half is an eigenvalue of a dagger a. And this particular vector n is also an eigenvector of a dagger a. Let us give a name to this particular operator, a dagger a. Let us call it as n cap. So it means that n cap acting on n is equal to en by h bar omega minus half n. We can call this whole thing as n, and we can write this entire thing as n cap acting on n is equal to nn, where n v is called as a number operator. So we have learned this, reviewed these simple basic things about the quantum harmonic oscillator. There are a few important notes before we move ahead about the quantum harmonic oscillator. The first thing is that the energies are quantized in the quantum harmonic oscillator, unlike that of the classical harmonic oscillator. What I mean by quantized is that there are only some permitted energy levels of the quantum harmonic oscillator which are allowed, unlike in the classical case where all energy possible energies are allowed for that harmonic oscillator. The allowed energies are given by this formula, where n is that what I had given you. From here we get this formula. So these are the allowed energies in the quantum harmonic oscillator. Second, the lowest energy is for n equal to 0, and it is given as En equal to h bar by 2. This is called as the lowest energy. The third is that the energy levels in this simple harmonic quantum harmonic oscillator problem are equally spaced. So if I plot the potential, that is half m omega square x square, in terms of x, then I would see that the allowed energy levels are all equally spaced. So this is E0, E1, E2, and so on. You see that E equal to 0 is not an allowed energy level for the quantum harmonic oscillator. So quantum harmonic oscillator can never be at energy equal to 0. The lowest allowed energy level is E0, which is equal to h bar by 2. That is this one. Let me write it down. The lowest achievable energy in a quantum harmonic oscillator is at n equal to 0, and it is half h bar omega, and it is called as ground state energy. It is called as the ground state energy. Now, because of this, or also it is also called as the 0 point energy. Now, because of the 0 point energy, the position and momentum of the quantum harmonic oscillator in the ground state are not fixed as they would be in a classical oscillator, but a small range of variance in accordance to the Heisenberg's uncertainty principle, we will come to it, is there. Now, coming to the important point, that is the second quantization of light, let us understand about the history behind this second quantization of light. Before the development of second quantization of light, light was often treated semi-classically. In semi-classical physics, light was described as a classical electromagnetic wave, while matter, such as atoms and electrons, were treated quantum mechanically. You can look at this particular table here. In the semi-classical treatment, the atom was quantized, but the light was considered a classical electromagnetic wave. Now, this approach was successful in explaining many phenomena such as the propagation of light through transparent media, the reflection and refraction of light at interfaces, and the interference and diffraction patterns which were observed in experiments in those times. However, semi classical theory had its own limitations, particularly when it came to explaining phenomena involving the interaction of light with matter at the quantum level. This particular semi classical theory failed. For example, semi classical theory it struggled to explain phenomena like photoelectric effect and the black body radiation, which required a quantum mechanical description of light. Even though we had laws and understanding about photoelectric effect and black body radiation, but we didn't understand how these phenomena occurred at the basic level. This required the quantum mechanical description of light. Also, semi-classical theory could not fully account for phenomena such as spontaneous emission, which you may have studied while studying lasers, where an atom emits light without external excitation, or the quantization of light intensity observed in experiments like the photoelectric effect or the Town Swiss TWIS experiments. Now, the phenomenon of second quantization, when it was developed, it provided a more comprehensive framework for describing the behavior of light at the quantum level. And by treating light as a collection of quantized particles, also called as photons, and representing the electromagnetic field quantum mechanically, second quantization, it allowed for a deeper understanding of phenomena which involved interaction of light with matter. Now, this approach, which is fully consistent with the both quantum mechanics and special relativity, has been crucial for advancing our understanding of fundamental processes in physics, and has led to significant technological advancements in many fields. So now, in this second quantization, we will consider that the atom is also quantized, as well as the light is a quantized field rather than a classical electromagnetic wave. Now, the history of this second quantization it traces back to the early 20th century with the development of quantum mechanics and the recognition of light as consisting of discrete packets of energy called as photons. However, it was not until the mid 20th century that the formalism of second quantization was fully developed. Now, this development was greatly influenced by the broader advancement of quantum field theory, which is a advanced version of quantum mechanics and its application to various fields of physics. The formalism of second quantization of light emerged as a way to describe the behavior of photons within the framework of quantum mechanics, treating them as quantized excitations of electromagnetic field. Now, the key contributions came from physicists like Dirac, Heisenberg, Feynman. In fact, there is a very nice popular science book written by Feynman, which explains quantum electrodynamics. That is the theory developed by second quantization of light, and I highly recommend you to check it. Now, they laid the foundation of the quantization of light, and the formalism found its applications in many fields. So, let us just have a broad overview of the differences. Now, in the semi classical treatment, we used classical electromagnetic waves, E bar and B bar. These are called as vector fields, yeah, to describe the phenomena in the semi-classical treatment. However, in the quantum version, we consider operators a cap and a cap dagger. I'll come to it for describing the electromagnetic waves. The second thing is that in the semi-classical treatment, matter was treated quantum mechanically, but more not light. But in second quantization, matter is also treated quantum mechanically, and the light is also treated. We had wave-like representations as ext and bxt in semi-classical treatment, but here we will have a particle-like description in the second quantization of light. Another important note is that there is, in the absence of light, the vacuum is considered to be nothingness and there is nothing of value over there. But in the second quantization of light, we can see that even if there is vacuum or there are no particles, there is something called as quantum vacuum fluctuations, which in fact has experimental observations. Now, there is the description of light in this description of light propagation in the semi-classical treatment is done through what are called as the Maxwell's equations. But in the second quantization, we use the quantum electrodynamics to describe it. So these are the light matter interactions that we can describe, and these are ones in the second quantized form. These are a few phenomena which we can describe using second quantization. For example, photon anti-bunching, which will come to later, entanglement, and so on. Now, second quantization of light has helped to resolve all of these issues which we had about understanding some physical phenomena. For example, the explanation of the photoelectric effect. It provided a theoretical framework for understanding the photoelectric effect, where light incident on a material surface it ejects electron by treating light as quantized photons. Second, quantum theory of coherence. So, second quantization helped develop the quantum theory of coherence, which describes the statistical properties of light. Through this second quantization, phenomena such as photon bunching and photon anti-bunching, we'll come to it when we will study the photon statistics. Which characterize the correlations between photons in coherent and non-coherent states, respectively, which were observed in some experiments. They were explained using the second quantization of light. We could understand the light matter interactions in more detail. A new field was developed, which is called as quantum optics. It helped in quantum information science. The second quantization helped in the quantum information sciences. And also there were so many experimental confirmations of what we had studied. So let us understand the second quantization in more detail.